But if you have a whole lot of copper chloride, then the copper chloride might not be the limiting reagent instead of like the aluminum being the limiting reagent or whatever. I don't know. All right. So in that practice for Monday, if you need a copy, there's one sitting up here. But number 2, this is exactly the same kind of thing as what we did in the lab in a couple different ways. You got so much of one chemical, 25 grams of lead 2 nitrate. You have 15 grams of sodium iodide. So we got 2 reactants, lead nitrate and sodium iodide. It could be that you've got the exact amount so that they both get used up to make the product you're looking for, but one of them is probably a limiting reactant, one's probably the excess reactant. There are practical reasons to intentionally not have equal amounts. In the case of the aluminum and the copper chloride, if we're trying to make copper and have no aluminum left over in with it, then you definitely want aluminum to be the limiting reactant. If instead, if you were to keep putting aluminum foil in with that copper chloride, eventually you're going to use up the copper, and instead of just filtering out just copper, you'd have aluminum mixed with it. Now you got aluminum and copper mixed, and separating the aluminum from the copper is not easy to do. That's incredibly difficult. So it's a whole lot easier if you're trying to make copper from reacting aluminum and copper chloride to intentionally have less aluminum than the copper chloride, because then you know that the solid product you're going to get is only going to be copper. There's not going to be any like aluminum so long as the reaction goes well. Anyway, the plan always is to take the quantities of the 2 chemicals or 3 chemicals or whatever that you know as reactants and convert both of those quantities into the quantity of the product that we're interested in or we're trying to make. So we know we've got 25 grams of this and 15 grams of this. And the question is, how many grams of sodium nitrate do we make? How many grams of sodium nitrate? So what you always do then is convert the quantity of each of the chemicals into the mass of the sodium nitrate. So I'm going to convert 25 grams of lead nitrate into grams of sodium nitrate, and then also convert from grams of sodium iodide into grams of sodium nitrate. And you compare the quantities of the 2 chemicals, or the 2 quantities of sodium nitrate, and whichever the masses is the least, that reactant must have been the limiting reactant. So, and all the time, if you start with a mass or a volume or something else, you always convert it into moles. There's no real exception to that. So the very first thing, if you see like a mass, you got to convert that into moles. So you got grams of lead nitrate, 1 mole of lead nitrate, PbNO3 2. I don't know what that comes out to be. Let's see. I got a lead 207.2 and 2 nitrogens 28.02 and 6 oxygens 6 times 16. Oh, I see what I did. 207.2 plus 28.02 and 16 times 6, 331.22. So you've converted from grams of lead nitrate into moles of lead nitrate, and then you use the mole ratios in the balanced chemical equation. You got to double check to make sure the equation is balanced. And in this case, it looks good. We got 1 lead on the left, 1 lead on the right. There's 2 nitrates on the left. And then because there's a 2 in front of the sodium nitrate on the right, there's 2 nitrates on the right. There's 2 sodiums on the left and 2 sodiums on the right. So the mole ratio is for 1 mole of lead nitrate, you get 2 moles of sodium nitrate. because there's just a 2 in front. And then because we're interested in how many grams of sodium nitrate, you then convert from moles of sodium nitrate into grams of sodium nitrate. So it's whatever the mass of sodium nitrate is. 22.99 plus 14.01 and 3 times 16. That's 85 exactly. And that gets you a mass. So 25 divided by 331.22 times 2 times 85, 12.8 grams. So this calculation predicts that if you have 25 grams of lead nitrate and if sodium iodide is in excess, you would make 12.8 grams of sodium nitrate. Then you got to repeat the same calculation, and most of it's the same, the concept, with the sodium iodide. I got 15 grams of sodium iodide. So 126.9 and 22.99. That's 149.89 grams of sodium iodide is the mass for 1 mole of sodium iodide. And then in the equation, for every 2 sodium iodides, you get 2 sodium nitrates. So for every 2 moles of NaI, you get 2 moles NaNO3. The last conversion factor is exactly the same, because again, you're converting from moles to grams. Let's see, 85.00 grams sodium nitrate. .5 grams. With 3 significant figures, 8.51 grams. So the amount of sodium iodide that's available gives you less sodium nitrate. And it's not necessarily because 15 is smaller than 25. Sometimes you'll have less mass of one than the other, but the one with less mass is actually not the limiting reactant. It depends upon the formula mass and also depends upon the mole ratio. So the limiting reactant is sodium iodide. And you would expect to produce 8.51 grams of sodium nitrate. That's the actual amount of sodium nitrate that is made. So how much of the non-limiting reactant is going to be used? The lead nitrate, you're not going to use up all 25 grams of lead nitrate. You're going to use some of it, but not all of it. And the trick there is to take the amount of sodium nitrate that you predict you should actually make and convert that back into a mass of sodium nitrate or lead nitrate. So really, you take this exact same work, just like this one, and do it in reverse, but switch out the mass. So instead of 12.81 grams, 12.8 grams, you can start with 8.51 grams. So if I write, I'm going to actually write it up in this space. 8.51 grams is the mass of sodium nitrate I expect to be able to actually make. I want to convert that into a mass of lead nitrate. So really it's these 3 conversion factors, but in reverse. They're flipped upside down and they're out of order. So because this last conversion factor got me from moles of sodium nitrate to grams of sodium nitrate, this same conversion factor can get me from grams of sodium nitrate back into moles of sodium nitrate. So I can be like 85.0 grams of sodium nitrate is the mass of 1 mole of sodium nitrate. And then this mole ratio is the same mole ratio, just put it upside down. For every 2 moles of sodium nitrate, I should need 1 mole of lead nitrate, NO32. And then I got to convert from moles of lead nitrate into grams. Same conversion factor, but it's going to be upside down. 1 mole of lead nitrate, NO32, has a mass of 331.22 grams. So I should expect it to be less than 25 grams. I'll show you another shortcut here in just a second, but 8.51 divided by 85 divided by 2 times 331.22, 16.6 grams. That's the mass of lead nitrate that you would need. But here's another trick. There's a ratio of the mass that you need or that you would use to get a mass of any kind of product. So like 25 to 12 is the same as the ratio of what to 8.51. And this is another way to do it. If you can think of it this way, 25 grams to 12.8 grams must be equal to something x divided by 8.51 grams. And if you solve for x, it should come out to also be 16.6. 25 times 8.51 divided by 12.8. Yeah, 16.6. If you can think about it like proportionally in that way. But the smarter way is to just take the mass of sodium nitrate you predict should be made and convert that mass of sodium nitrate back into a mass of lead nitrate. So you'll see that really like these three steps, this one, and this one, those three steps are exactly the same as these three steps. They're just reverse the order and everything's flipped upside down. So you've already kind of written down all the stuff to be able to do all the work. So this is how much is needed, how much lead nitrate is needed. How much lead nitrate you'd have left over is, because you start with 25 grams lead nitrate and you figure you should use 16.6, how much is left over is whatever 25 grams minus, it's 25.0, it says 0.0, minus 16.6 grams. That'll tell you like the amount of lead nitrate that would be left. 25 minus 16.6, 8.4 grams. PbNO3, 2 remains. So that's how much lead nitrate you need, the 16.6 grams. And how much lead nitrate would be left over is however much out of the 25 you end up not using up. Well, that's not going to work. I'll just put it on top for now. It probably won't take you there. You know, we'll never run out of QR codes. I forget. I read a thing about how many possible QR codes there are. And like, we could never. Yeah, it's 2 to the power of the number of squares on there. Aren't there like 20 by 20? So there it's like 2 to the 400th power, which is like the biggest number ever. Not the biggest number ever, but isn't that amazing? Never run out of QR code. I mean, you can't say never, but yeah. And everyone's unique from the last one. So, because it wouldn't work if you had a QR generator that had a non-unique QR code. So QR codes are actually randomly generated, but the probability of any two QR codes ever being the same approaches 0, so they're never the same. If you accidentally get a QR code generated the same as another one, we'll just do it again, and then it'll be different. The 3 big boxes in the outside corners, that's so your device can tell which way it needs to be. Because it turns out even if you make it and you flip it the other way, your device will figure out that it was actually like backward or upside down or mirrored. It uses the orientation of the three big boxes to orient the other individual code sectors. You could have a QR code that would be totally blank. You could also have one that's just totally black. But yeah, there's so many permutations, it's crazy. All right, so that one's okay. And then this one is actually a salt reacting with sulfuric acid, sodium chloride and sulfuric acid. So you got 10 grams of sodium chloride, 12 grams of sulfuric acid. How much HCl forms? So we're trying to figure out the mass of HCl. So in both cases, you take the mass of something that you know, 10 grams of sodium chloride. First thing you always do, if you're not in moles, is convert to moles. So you got 22.99 and 35.45. That's 58.44 grams. It's the mass of 1 mole, always 1 mole. And then you need to check to see if the chemical equation is balanced. And there's 1 sodium on the left, 1 sodium on the right. There's 1 chlorine on the left, 1 chlorine on the right, 2 hydrogens on the left. And there's 2 hydrogens on the right because there's 1 here and 1 there. And then there's 1 sulfate, the SO4, 1 SO4. So it is just a mole ratio. Everything is 1 to 1. 1 mole NaCl gives you 1 mole HCl. And then to get the mass of HCl, every mole of HCl just has a mass that's equal to its formula mass, 36.46. This one's a little bit quicker to do because the masses are easier to figure out. The mole ratio is just 1. 58.44 times 36.46. This is 6.24 grams. And then what if you have 12 grams of sulfuric acid? So once again, you take the mass of sulfuric, the H2SO4, and usually that's a solution, and we'll deal with how that works. But for now, just that it's a mass of H2SO4. You got 2.02 for the H. Sulfur is 32.07. And then 4 oxygens, 98.09. It's the mass of a mole of H2SO4. The mole ratio for H2SO4 to HCl is also 1 to 1. And the last step's exactly the same, because again, you're converting from moles of HCl into grams. So there's a greater mass of H2SO4 than sodium chloride, greater mass of sulfuric acid than sodium chloride, but the formula mass for sulfuric acid is bigger than sodium chloride. So it's not certain that sodium chloride is the limiting reactant. In fact, in this one, it won't be. This is 4.46. HCl. So the how much HCl actually forms is the smaller of the two quantities. This is what actually forms. That makes H2SO4 the limiting reactant. And how much excess reactant is not consumed. So just like in the last example, this mass of HCl that's actually made, you can convert that into the mass of sodium chloride that's needed. So once again, you can take this mass that's actually made, 4.46 grams of HCl, and convert it into a mass of sodium chloride. And that'll tell you how much sodium chloride was needed to produce this HCl, and it also helps you predict how much was left over. So it's the same 3 steps, but they're in reverse and they're upside down. This is going to be 36.46 grams for 1 mole. Every 1 mole of HCl, you need 1 mole of NaCl. And then every 1 mole NaCl has a mass of 58.44 grams. .15 grams. So this is the mass of NaCl that's needed or like will be consumed out of the 10 grams that you're starting with. So how much excess reactant remains if you subtract the 7.15 grams of sodium chloride that remains from the 10 grams that like you started with, you'd end up with like 2.85 grams of NaCl remains. You know, the copper chloride that you reacted with the aluminum is like blue in color, and it was the excess reactant. So once you were done with the reaction and the filtering, that solution that you're left with should have still been like a greenish blue color. It's possible you actually were pretty close to the aluminum being non-limiting. But sometimes we can use the color of the reactant to indicate whether or not the like right amount of product has actually formed or not. So that's how you do it. The other thing that you could end up having to do is maybe calculate a percent yield. You know how to do that now too. So let's say you expect 4.46 grams to be produced, but maybe only 4.21 grams is actually made. When you divide the mass that's actually produced by the mass that you would expect, that gets you like a percent yield. So this might be like a 94.3% yield, meaning like if this is the actual amount that's produced from what you expect, that gets you a yield it's good. It is what it is. It tells you that like, I don't know, some side product. What a side product is in this theoretical reaction, sodium chloride and H2SO4, we predict these two products and those two products only, but there are other products that could form during the reaction. Like because there's sulfuric acid, you could, if the solution's a little bit basic, some of the hydrogens could end up going with hydroxides to make some water as part of a neutralization that also takes place. That depends on if the sodium chloride is solid or if it was aqueous. You can also like in the filtration, some of the copper could have like worked its way through the paper and you lost some of the copper, and that got dumped down the drain instead of weighing it. And sometimes the yields are too high because you have a contaminant. So with the copper chloride and aluminum experiment from Tuesday, that paper ends up to be all kinds of different color because you got like other stuff that's soaked into the paper that adds to the mass of the paper. Despite the fact the paper is dry, there's some new crystals that are formed within the paper that's kind of a mess. That happens. All right, so the review problems are a pretty good set of like things that you should be able to do. If you need to let's see, finish up the baking soda lab, or there's one more product on the middle table. I don't know whose it was, like a filter paper with the stuff in it. I don't know where it came from, but it's sitting on the middle table still. So if you didn't weigh your thing from yesterday, I can get a balance out so you can weigh it. All right, so questions, confusion about stuff. What do you need to know about? Always have a periodic table and a calculator handy, but you work on these now and finish them up before tomorrow, and then we'll go over them during class tomorrow. We made it through another week, I guess. Oh, I got to do attendance. Let's see, stop. Oops. Share screen.